Imagine you could step into a machine tonight and come out in the year 2126. For you, only a few minutes have passed, but outside, an entire century is gone. Everyone you knew has grown old or disappeared. Cities have changed, countries may have changed. The world moved on without you. We would call that time travel. And strangely enough, physics already knows how to do something very close to it. The problem isn't getting to the future. The problem is getting back. For most of human history, time seemed simple. A second was a second. Whether you were standing still, riding a horse, crossing an ocean, or watching the stars, somewhere behind everything there seemed to be one universal clock, counting forward at the same rate. Then Einstein changed that. Space and time aren't two completely separate things. They're connected as space-time, and the way you move through space affects how much time you experience. If two people move differently, they can eventually meet again, having experienced different amounts of time. This sounds like one of those ideas that only exists on a blackboard, but it doesn't. Relativistic time dilation has been measured with atomic clocks. Satellites have to account for relativity. Even astronauts experience tiny differences in elapsed time compared with people on Earth. Normally, the difference is absurdly small, but increase the speed enough and it stops being small. Imagine two twins. One stays on Earth, the other boards a spacecraft capable of traveling extremely close to the speed of light. To the traveler, life aboard the ship feels completely normal. Their heart beats normally, their thoughts aren't slowed down, their clock ticks once every second exactly as it always has. But when they return to Earth, something is wrong. The twin who stayed behind may have aged decades. The traveler may have aged only a few years. They didn't freeze themselves. They didn't sleep through history. They simply followed a different path through space-time. And in a very real physical sense, they traveled farther into Earth's future than everyone around them. So if your goal is only to see the future, nature has already given us a time machine. It's called speed. Unfortunately, it comes with a limit. The speed of light in vacuum is about 300,000 kilometers per second. You can accelerate a spacecraft closer and closer to that speed. Half the speed of light, 90%, 99%, 99.99%. But every step becomes harder. For anything with mass, reaching the speed of light itself would require an unbounded amount of energy. So, according to special relativity, a normal spacecraft can approach that wall forever, without actually crossing it. And this is where the speed of light becomes more interesting than an engineering problem. Because it isn't like the sound barrier. For a long time, humans couldn't travel faster than sound. Then we built better aircraft, and did it. It's tempting to imagine light speed the same way. Just another challenge waiting for better technology, a better engine, a better fuel, a more advanced civilization. But the universe treats light speed very differently. If you could somehow send information faster than light, the problem wouldn't simply be that you arrived somewhere very quickly. Under the rules of relativity, you could begin to interfere with the order of cause and effect. And that's where time travel becomes dangerous. Suppose you're on Earth and your friend is on a distant spacecraft. At noon, you send them a normal radio message. Radio waves travel at light speed, so your friend receives the message later. You send it first, they receive it second. Cause, then effect. Everything seems perfectly normal. Now imagine we've invented some impossible new technology that sends messages faster than light. At first, this sounds harmless. Your friend simply gets the message faster. But relativity doesn't give the entire universe one universal definition of now. Two observers moving relative to each other can disagree about the timing of distant events. As long as information moves at or below light speed, that disagreement doesn't allow you to casually send information into your own past. But faster-than-light communication can change the situation. With the right arrangement of observers and return signals, you could create a scenario where the reply arrives before the original message was sent. You sit beside the machine at 10 o'clock. At 9:59, a message appears. Don't send the message. So at 10 o'clock, you decide not to send anything. But then, who sent the warning? That's the strange thing about faster-than-light travel. The speed itself isn't necessarily the most frightening part. The frightening part is what happens before, and after. We usually imagine the speed of light as a cosmic speed limit. Maybe that's incomplete. Maybe it's also a causality limit, a boundary that helps keep causes on one side and their consequences on the other. But humans are very good at looking for loopholes. If we can't move faster through space, what if we take a shorter route through it? Imagine two cities separated by a mountain. You can drive around the mountain or dig a tunnel straight through it. You haven't made the car faster, you've made the journey shorter. A wormhole is the space-time version of that idea. 2 points enormously far apart through normal space could, theoretically, be connected by a much shorter passage. You enter one mouth and exit the other. Locally, you never have to exceed light speed. You cheat the distance instead. Wormholes are allowed by certain solutions of general relativity, although that doesn't mean we know whether usable ones actually exist. Keeping a traversable wormhole open may require conditions we don't know how to create. It may be unstable. Quantum effects may destroy it. But suppose, just for a moment, that an advanced civilization manages to build one. Then things become interesting. A wormhole has two entrances. Let's call them A and B. Start with their clocks synchronized. Now take entrance B on a journey at extremely high speed and eventually bring it back. Because of relativistic time dilation, less time may have passed for B than for A. From the outside, the two entrances are now separated not only in space, but also in time. Yet, through the wormhole, they're still connected. Walk through one side under the right conditions, and you could emerge from the other at an earlier external time. The tunnel through space has become a tunnel through time. This is one reason wormholes appear so often in discussions of theoretical time travel. Not because physicists secretly know how to build one. They don't. But because Einstein's equations sometimes seem to leave loopholes. And wormholes aren't the only ones. General relativity contains mathematical solutions with something called a closed timelike curve. The name sounds complicated. The idea isn't. Imagine your life as a line through space-time. Yesterday leads to today. Today leads to tomorrow. Normally, that line never bends back toward its own past. A closed timelike curve does. You keep moving forward according to your own clock, but the geometry of space-time eventually carries you back to an event that happened earlier. No rewind button, no reversing your heartbeat. You always move forward locally. It's space-time itself that loops. Physicists have found this kind of behavior in several highly unusual theoretical situations involving rotating universes, rotating black holes, cosmic strings, idealized cylinders, and wormholes. But there's an enormous difference between saying, the equations contain this solution, and saying, we can build this. Many of these ideas require absurd conditions. Some need infinite structures. Some are unstable. Some may be hidden behind regions you could never escape. Others might disappear once quantum mechanics is included. But their existence creates a deeper problem. If traveling into the past is truly impossible, where exactly does physics forbid it? And once you ask that question, you run directly into paradoxes. The famous example is the grandfather paradox. You travel into the past and prevent your grandparents from meeting. Your parent is never born. You are never born. So you never travel back, which means your grandparents do meet, which means you are born, which means you travel back, and we're trapped. The loop contradicts itself. But there's another paradox that's even stranger, because nobody has to die. Imagine someone gives you a book containing the design for a time machine. You spend your entire life building it. When you're old, it finally works. You travel 50 years into the past and give the same book to your younger self. Where did the design come from? You received it from your older self. Your older self received it from you. Nobody wrote it. The information simply exists inside a loop. This is the bootstrap paradox, and it reveals something important. The real problem with traveling backward isn't distance. It isn't even energy. It's causality. How can something exist without an origin? How can an event prevent the event that caused it? Reality needs an answer, and there are several possibilities. None of them are particularly comfortable. The first possibility is that you can travel to the past, but you can never change it. This is associated with the idea of self-consistency. You go back to prevent an event. Something stops you. The gun jams. You arrive too late. Or worse, your attempt to prevent the event becomes the thing that causes it. History doesn't rewrite itself because your trip was always part of history. If you meet your younger self tomorrow, then from your younger self's perspective, that meeting always happened. There was never another version. No original timeline to overwrite. The paradox disappears. But free choice starts looking strange. You may feel completely free to act, yet whatever you choose must somehow remain consistent with what already occurred. The second possibility is branching timelines. You return to 1990 and change something, but you don't erase your own history. Instead, reality branches, or you enter another branch. Your original world continues to exist. A second history grows from the change you made. Now you could kill your grandfather in that branch without erasing yourself because you were born in another one. The paradox disappears, but there's a price. Suppose you traveled back to save someone you lost. You may find a world where another version of that person survives, but the person in your original history is still gone. You haven't repaired your past. You've only found a reality where things happen differently. And then there's the third possibility. Maybe nature simply refuses to let time machines exist. Stephen Hawking called this idea the chronology protection conjecture. Perhaps whenever space-time gets close to forming a usable loop into the past, quantum effects become strong enough to destroy the setup. Maybe the wormhole collapses. Maybe the energy becomes uncontrollable. Maybe some deeper law of quantum gravity closes the door before causality can be violated. We don't know. And that is what makes the subject so fascinating. General relativity repeatedly seems to say, maybe. Then some other part of physics seems to answer, probably not. So, do we have any evidence? This is usually the point where time travel stories begin showing strange photographs. A person wearing modern-looking clothes in an old crowd. Someone apparently holding a smartphone decades before smartphones existed. People claiming to know the future. They're entertaining, but none of them are convincing scientific evidence of visitors from the future. The actual evidence is less sensational and much more important. We know time dilation is real. We've measured it. We know clocks moving differently through space-time can accumulate different amounts of elapsed time. We know gravity affects the passage of time. We know two people can leave each other, reunite later, and genuinely have aged by slightly different amounts because of relativity. So one-way travel into the future isn't speculation. The effect exists. Our problem is scale. We simply aren't fast enough to turn those tiny differences into centuries. Backward time travel is different. There is currently no credible experimental evidence that anyone has traveled from the future into the past. Only equations, thought experiments, possible loopholes, and paradoxes. Which brings us back to that strange cosmic wall. Maybe we've misunderstood the speed of light. We call it a speed limit because that's what it looks like to us. Nothing with mass can simply accelerate through it. But perhaps the deeper reason it matters isn't speed. It's order. Below that boundary, causes remain connected to their effects in a way that keeps reality understandable. Allow the wrong kind of faster-than-light travel, and that order can begin to break. A message may arrive before it was sent. A machine may contain information nobody created. A traveler may erase the reason they traveled. Maybe someday we'll discover new physics that solves all of this. Maybe wormholes exist. Maybe space-time can be engineered. Maybe our descendants will look at our understanding of time the way we look at ancient maps of the world. But there is another possibility. Perhaps traveling into the future is allowed because it doesn't threaten history. You can leave everyone behind. You can return after centuries have passed. But what happened still happened. The past remains untouched. And maybe that's why every theoretical road backward eventually runs into trouble. Not because our machines are too primitive, not because we haven't found enough energy, but because the speed of light may be protecting something more important than speed. It may be protecting the order of reality itself. And if that's true, the universe doesn't stop us from traveling through time. It only makes sure we can never take it back.